Hey guys, so today is the second lesson in the final unit. We're going to be going over what Earth's radiation budget is, and there's also some calculations associated with this. So Earth's radiation budget, for this we're going to be going over exactly what that means, the different factors that affect the Earth's radiation budget in different regions. So that includes things like albedo and angle of inclination. We're also going to talk about the effect of greenhouse gases, which I'm sure you're all very familiar with. Then we're going to talk about specific heat capacity, heat effusion, and heat of vaporization, each with which come with their own set of calculations. So solar radiation is a combination of different types of electromagnetic radiation. We talked about this briefly in the physics unit. So electromagnetic radiation includes visible light and UV radiation, both which are part of solar radiation that hits Earth here. Solar radiation can be either reflected or absorbed. If the radiation is absorbed, it gets converted into thermal energy. So whatever absorbs the solar radiation heats up. And things that are darker in color tend to absorb more solar radiation. This is why, like, black pavement gets really, really hot to the touch in the summer when it's really sunny. Some of that heat energy can then be radiated back out into space, which is why if you're standing above like black pavement in the middle of a parking lot, it'll feel much hotter than if you were, like, say, in a field. And some of that heat will be trapped and just remain in that object. Earth's radiation budget refers to the amount of solar radiation that's coming into Earth compared to the amount that is leaving. So the net radiation is just incoming radiation minus outgoing radiation. If the amount of radiation entering and leaving is the same, then Earth's energy will be balanced or at homeostasis and will not change. This means that the thermal energy of the Earth won't change and the Earth will not heat or cool. If more radiation is coming in than what is leaving, then Earth's energy will increase, meaning that Earth will heat up. And if, on the other hand, more radiation leaves than what is entering, Earth's energy will decrease and the Earth will cool. This is what has happened in the past with, like, ice ages and stuff like that. So 100% of the solar energy that comes towards Earth is going to be broken up into either the energy that's reflected, the energy that is, and the energy that's absorbed. So if we look here, obviously the atmosphere is going to reflect some of that, but not most of it. The clouds reflect even more, which is why on cloudier days, you don't tend to feel as hot. And then some of it can be reflected directly off Earth's surface. That is especially true in areas that the ground cover is really, really light, like on snow and ice. And then just over half of Earth's radiation is absorbed by the lands and the ocean, which is why Earth heats up. And then of that energy that's absorbed, much of it will be radiated back out into the atmosphere. And the hope is that all of it will, over time, kind of be radiated back out into space so that the amount that's incoming and the amount that's leaving is balanced. Now, the issue with this is that with greenhouse gases, what we have is that some of this energy that should be getting radiated back out into space instead gets trapped by greenhouse gases in our atmosphere and just gets turned right around and comes back down and just gets stuck hanging out in our atmosphere instead of radiating back out into space. The radiation budget of different areas of Earth will be different from one another. Some areas receive more solar energy than others. Specifically, the closer you are to the equator, the more solar energy is available. And then some areas reflect more while others absorb more, which we've already talked about. Areas with lots of snow and ice will reflect more of that solar radiation, while areas with lots of, like, pavement, like cities, will absorb more. So because of that, solar regions tend to have less insolation. Insolation, in this case, meaning the amount of solar energy that is entering, and they will have more reflection. Whereas if you have, like, say, a city near the equator, you're going to have high insolation, high amounts of solar energy coming in, and very low levels of reflection. So yeah, insolation is the amount of solar radiation that is received by a region, and it'll depend on things like latitude, so how far away you are from the equator, which ties into something called the angle of inclination. So latitude, like I said, is just how far a place is from the equator. Closer to the equator, more solar radiation. The Earth is also tilted on its axes. So if we look at this kind of globe here, the axis of the Earth goes through here and then comes out here on the bottom. So we're talking about this kind of an angle, which is actually a 23.5 degree angle. That's called the angle of inclination. So the tilt of the Earth on its axis is the angle of inclination. If you are in an area that's tilted towards the sun, then obviously you'll have more insolation. So bust this out again. So if this is the Earth, and say the sun is over here, right now the North Pole, which would be over here, is tilted away from the sun, whereas somewhere like in Africa would be tilted towards the sun. The angle of inclination is actually what causes our seasons. So during summer, that is when we are tilted towards the sun and therefore receive more solar radiation. During winter, we're tilted away from the sun, meaning that we get less solar radiation. And so because of the angle of inclination, the summer here in the northern hemisphere would be during the winter in the southern hemisphere, like when Australia is. So we have opposite summers and winters. It is important to note that Earth's orbit is like an elliptical, so kind of like an oval shape. So the Earth is closer to the sun during some months and further away in others. However, the distance of the Earth to the sun is not what causes the seasons. That's a really common misconception. It is just the angle of inclination, the tilt of the Earth on its axis, that causes the seasons. In fact, here in the northern hemisphere, we are actually furthest from the sun during the middle of summer, but that is when we're tilted towards the sun. So you can kind of see that in this picture here. So right kind of where this line is pointing here would be where we are in Canada. And so this is when we're pointed directly at the sun, and it's in the middle of summer, but it is when we're the furthest from the sun. When we're closest to the sun is actually the middle of winter, and that's because we would be up here tilted away from the sun. So we'd be like rotating around up at the top here, pointing away from the sun, depending on whether it's night or daytime. In the summer, we're up around here, pointed towards the sun. And then the opposite would be true for like Australia. Would be getting nice direct sunlight in their summer and would be pointed away from the sun in their winter. Okay, so solar radiation, the amount of insolation is very important in terms of regional radiation budget, but so is the amount of absorption or reflection that's happening. So albedo is the term that we use for reflectivity of an area. So higher albedo is higher reflectivity. So for example, the poles where there's lots of snow and ice would have really high albedo and low insolation, whereas a parking lot would have really low albedo because it has really high absorption and not a lot of reflection happening. Both atmospheric dust and clouds reflect solar radiation, so that can have a cooling effect. However, Clouds can also trap heat that's emitted from Earth's surface in that kind of like radiation. So following really large volcanic eruptions, when lots of dust is thrown into the air, that can reflect sunlight and cause cooling. However, lots of greenhouse gases are also released, which trap heat and cause warming. So in the past, usually following a large volcanic eruption, there would be an immediate cooling period because of how much the sun is blocked off, but there would be a long-term warming effect. So after the dust settles and the sunlight comes back in, the greenhouse gases remain in the air much longer, and therefore you have a warming effect as the sunlight comes in, now that the dust is gone, and that radiated heat gets trapped by the greenhouse gases. And at the bottom here I said, present day the net result is often cooling, and we'll talk about why that is in, I think, the next lesson. So reflectivity, again, light colored surfaces are going to reflect more, so have higher albedo. Dark colored surfaces absorb more, therefore have lower albedo. The albedo of Earth as a whole is decreasing due to a couple different factors. One is urbanization, which is essentially the building of more urban areas, which just means more parking lots, more roads, more dark buildings, all of that kind of stuff. Even like the shingles on roofs of houses tend to be dark. Also because of global warming, we have a lot of melting of our glaciers and polar regions, which means less of those high albedo areas of snow and ice. And things like agriculture, a plowed field is much more absorbing of energy than a forest would be. Yeah, okay. By the way, this idea that the more the Earth heats up, the more ice melts, the more ice melts, the more energy is absorbed because of less reflectivity, which means more heating, which means more melting, which means more energy absorbed. That's an example of a positive feedback loop. Essentially, a positive feedback loop is anything that kind of like snowballs and builds on itself. Okay, so greenhouse gases essentially affect the amount of energy radiated back out into space. Our atmosphere does have naturally occurring greenhouse gases, which stop heat from escaping and the Earth from getting too cold. So we do need some greenhouse gases in our atmosphere. However, if you have too many greenhouse gases in the atmosphere, that means less energy is escaping out into space, which means that overall the atmosphere and the Earth become warmer and warmer and warmer because it is essentially unbalancing Earth's radiation budget. The amount of sunlight coming in hasn't changed, but the amount of energy radiating out has. So that is what is essentially attributing to Earth's unbalanced radiation budget right now is the increase of greenhouse gases. Greenhouse gases include things like carbon dioxide, methane, nitrous oxide, sulfurous oxide, those kind of things. The oceans do reflect some solar radiation, but they absorb a lot of it as well. And the oceans absorb this energy, which becomes thermal energy, and then heats the ocean. Normally, water does heat very slowly because of something called high specific heat capacity, but the oceans are currently experiencing more warming than the land or the atmosphere because we have a lot of ocean area near our equators, and therefore they're absorbing a ton of solar radiation. So speaking of specific heat capacity, it is the amount of thermal energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. I don't really know, or sorry, I don't really care if you know that definition or not, as long as you know that specific heat capacity essentially talks about how well something absorbs energy. The formula is Q equals mc delta T, where the Q is the amount of thermal energy in joules, M is the mass of the object in grams, C is the specific heat capacity in joules per gram degree Celsius, And delta T is the change in temperature, also in degrees Celsius. Water, like I said, does have a very high specific heat capacity, which means it can gain a lot of thermal energy without increasing its temperature very much. This is why, like in the summer, the air heats up a lot faster than the water does. It takes a really long time for like a lake to get warm compared to the atmosphere. And then vice versa, like the ground will freeze before a lake will freeze in the winter. The specific heat capacity for water is 4.19. So let's do some practice questions here. Okay, so for the first question, it says how much thermal energy is needed to warm 50 grams of water from 25 to 50 degrees Celsius. So the thermal energy is our Q, that's what it's asking for. Our mass is 50 grams. C, when we're talking about water, is always 4.19. And then our delta T is the final minus the initial. So 50 minus 25 degrees Celsius. So I'll do that part first, obviously just 25, and then we'll multiply those together. So 50 times 4.19 times 25 is 5,237.5. Didn't see that decimal in there. And our units would be joules when we're talking about energy. Okay, so pause here and then see if you can calculate the second one on your own. Okay, so for the second question here, again, I'm going to start with my Q equals MC delta T formula. I plug in my 800 joules where the Q is, my 100 grams for the M, and my 4.19 for the specific heat capacity. And then even though I am given one of the temperatures, I am going to leave this as just delta T for now, just because I find that the easiest way to go about solving this. Then I multiply my 100 by my 4.19 to get 419. And then I'm just going to divide by 419 to isolate the delta T. So 800 divided by 419 is 1.91-ish is my delta T. Then the second step is going to be to use what I know of delta T. So delta T is always the final minus the initial temperature. I'm going to plug in my delta T value that I just solved for. And then it says I heated the water from 5 degrees Celsius. I want to know the final temperature. So I'm looking for my TF, and I'm going to plug in my initial of 5. And then in order to isolate the TF, I just have to move the 5 to the other side because right now it is a minus 5. I will add 5. And we will get 6.91 degrees Celsius as our final temperature. Okay, in order to change the temperature of a substance, you have to either add or remove energy. Adding energy will heat the substance, removing energy will cool the substance. And then if you're going to actually push it through a change of state, that's going to require even more energy. So changes of state are things like melting, freezing, vaporization, condensation, evaporation, all that kind of stuff. Sublimation. So heats of fusion and heats of vaporization are the amount of energy required for some of these changes of state. So heat of fusion is the amount of energy that a substance has to absorb in order to melt. Heat of vaporization is the amount of energy that must be absorbed in order for a substance to vaporize. And for both of those, we're dealing with 1 mole of the substance. The formula for both of those is the heat of either fusion or vaporization is equal to the Q value, which is the amount of thermal energy, this time in kilojoules, and divide that by the moles, which we represent as N. Just a reminder from the chemistry unit, moles is equal to mass divided by molar mass. Molar mass is just the combined atomic masses of all of your atoms. So knowing that, let's go through these two practice questions. Okay, so this first one is fairly straightforward. It's asking for the heat of fusion, so our H value. It tells us the amount of thermal energy that is added, which is our Q value, so that is 27.05 kilojoules. It also tells us our moles, which is our N value, is 4.5. So for this one, all we do is divide 27.05 divided by 4.5, which is 6.01 repeating. The second one is a little bit trickier because it's going to require more than just one step. Okay, so for this one, it's still asking for the heat, in this case of vaporization rather than the heat of fusion, but we still use the same formula for that. It's still Q over N. But this time, while we are given our Q value of 340, we are not given our N. We have to find that first. So our actual very first step here is going to be to find the molar mass of water. Now, in order to do that, you need to look up the molar mass of oxygen, which is just 1. We times that by 2 because there's 2 of them. And then we add the molar mass of oxygen, which is 16. So you're going to get 18. The molar mass of water will always be 18. And for some of you, it might be easier to just memorize that than have to calculate the molar mass of water. The second step is then to calculate the moles. So moles equals mass over molar mass. We were given the mass of water as 150 grams. So I'm going to do 150 divided by 18, which gives me 8.3 repeating for my amount of moles. Now I can go back to my heat of vaporization formula and do 340 divided by 8.3 repeating. 340 divided by 8.3 repeating, and I get 40.8. And sorry, I should have wrote my units over here. It is kilojoules per mole. So that would be my final answer. So really, this isn't a tricky type of calculation. The only thing to remember is that in order to plug in your moles, you may need to calculate the moles. You cannot plug in mass where that N value is. Okay, that is it for today's lesson. Let me know if you have any questions.